Good morning, everyone. I've been asked to talk a little bit more about the structured error model, about nuclear reactions, cold fusion, etc., or rather in one word, alchemy. As Adrian reminded me this morning. So in effect it is alchemy, because we're talking about transmutations of the elements, right? So I wanted to touch upon a few slides I had already shown in the main presentation in Bath. And I would like to start with the hypothesis again. The hypothesis, of course, well, you can read it, but I'll read it for you. Could it be that the heavier elements are created in situ on the Earth itself through what is known as Lennard, and that these processes are the cause for geological processes such as volcanoes and explain the abundance of the elements? So this is what I want to zoom in this coming half an hour or whatever. Why is this important? Yeah, if you can, just a little bit. Thank you. So, when we're talking about the elements and the creation, as I pointed out, the current main prevailing thought is that they were created initially in the Big Bang, merging stars, exploding neutron stars, exploding white dwarfs, etc., etc., etc. When we look at the EU paradigm, we need to come up with a different answer. So basically, alchemy is back in the game. What we see here is the black smoker. There are a gazillion of them underneath the oceans, and they are often very black due to the high sulfur content. So I wanted to zoom in a little bit more. James, if you can go to the next page, please. Now, what is going on? We have a hydro cycle. Water is coming to the Earth in one way or the other, or it was brought in the past, it doesn't really matter. Water is constituents, of course, H2O. Everybody thinks when we're talking about fusing hydrogen together into helium, because that is a huge, lovely energy gain. That's why we really, as human beings, want to find that one. So the fusion reactors like the tokamak in the south of France, they're really focusing on that particular thing. When you look at alchemic or cold fusion reactions, we get a totally different picture. We can now see that the oxygen, for example, is the fuel. The oxygen is what fuses together. So what do we have? We have a huge ocean basin where water seeps in. Water seeps in through the Earth, and it allegedly, of course, only boils and takes along some minerals that are dissolved, and then they separate a little bit, and they come out as certain gases. But the abundance of sulfur at those black vents, we're talking 10, 20, 30%, constantly, all of them. Volcanoes are known about this. When we have an electric strike, for example, it's always been associated with the smell of sulfur, the devil, right? What we're looking at is the fact that elements may actually be transmutating here on Earth underneath our feet, explaining also the anomalous heat in the center of the Earth, or at least as one of the potential mechanisms to cause heat underneath our feet, create magma. Can you go to the next slide, please? As you can see, there are about everything which is red here, the lines, is where the volcanic activity predominantly is. The volcanoes on Earth, about 1600, almost always associated with the sea, meaning very much on the edge of the water. Japan, Alaska, the Philippines, you name it. So, water is connected to volcanic activity. We cannot ignore that. James yesterday, the day before, pointed out in his geological talk that there are about 4 planetoids or moons in our solar system that show comparable geological activity as the Earth, and they're all water related. So meaning, I believe the water is actually the fuel, or rather the oxygen. So oxygen and an oxygen becomes a sulfur, creating sulfur all the time. Not only that, it creates excess heat, just like in the Lennard processes is talked about. We need to come up with this new cosmology, because it's a new cosmology. I heard the term just before. It's a new cosmology. We need a new cosmology. We cannot explain the abundance of the elements the way we do right now. Plants and animals, biological transmutations, is a big, big component. In fact, I believe the abundance of the elements are all related to the process I'm alluding to now. Could you swap to the abundance, please? So what we see here is a list of, generally speaking, depends on what you look at, the Earth's crust, the solar system, or the universe as a whole, but generally speaking, this is the picture that more or less emerges. So what we see is, of course, hydrogen, way on the left, is the most abundant element in our universe. And then comes helium. Helium is created from the hydrogen. Then suddenly the lithium, beryllium and boron are always depicted as being quite anomalous, and they are only created in a little bit of intergalactic cosmic radiations, etc., because they're so low in abundance. And then we see carbon jumps up already. Now, after that, nitrogen drops a little bit, oxygen goes up. Now, I hope you can all see a trend later on that it zigzags, right? Goes up, goes down, goes up, goes down. What's the explanation there? How come? Why is that so? When we look at how they are created, can you go back to the presentation? When we look at how they are created, when we look at how they are created, we start at our sun, our star. It's allegedly, and I believe so, at least to a large extent, it's of course hydrogen over there. Hydrogen fuses together into helium. I believe that the stars are basically creating the first lighter elements, like the helium, on the stars themselves. But the next step, and this is a crucial one, which I keep pointing out, is the carbon. Carbon is very special. It's the center of everything. It's the center of life. It's a phenomenal substance to start with. Even in the atomic structure, we can see that is the repeating maximum shape. As I keep pointing out, it's an icosahedron, maximum platonic solid, if you will. So it's important. Now the stars create this carbon element, which is the basis for life. Stars are seeding the rest of the solar system, the universe, with the building blocks for life to exist. These nucleates, these carbon nucleates, whether it's a carbon or a little bit bigger like an oxygen, that thing is most important. Without that, you cannot do what we call the cold fusion or the alchemy. It needs to be created, apparently, predominantly in the stars. It accumulates on the Earth. So what do we get? Over here on the left we see the hydrogen, helium becoming a carbon. The helium and a carbon, and I'm not sure how and why, if it's happening on the star itself, or in the solar wind, or in the corona maybe, that's for measurements and all that stuff. And this data is not clear. If you try to find sensible information about this, it's very, very difficult. Usually they just focus on a few isotopes of one specific element, and then they try to fit that into some cosmological dating system, etc. I believe the stars are seeding planets. Planets get the carbon, get the water. That's when all the other heavier elements, I believe, are created, more or less in situ. In situ meaning on the planet themselves, creating the rocky material, creating the gold in the quartz veins, creating the sulfur in the magma processes, probably deep underneath our feet. Now, if we look at, can we go back to the ones, please, for a moment? Yeah, this one is good. The white ones over on the left picture, we see some peaks there, and we can see the carbon, the oxygen, and a few others, like the magnesium and the silicon. They are overly abundant. And the other picture we saw before was this little zigzag. Now what happens? We have certain building blocks. Those building blocks are available, and we can work with them, create a next one. That means that's the logical step. There are certain steps throughout the periodic table that can create new elements. So, we get a helium, created in the stars. We get a carbon, created in the stars. They fuse together, becoming one oxygen. That process keeps repeating. But now, oxygen, as we know, is the most abundant element on Earth. Absolutely the most abundant. Half the crust is more or less oxygen. All kinds of metal oxides. If we look at the abundance again, the zigzag, that means certain elements combine readily together, and certain are very low in abundance already to start with, so you get a different combination. That's why every time you see the zigzag, it drops, and the next one is the more logical one, because those building blocks are there, and you get the next one. So the helium, very abundant, The carbon, very abundant, but used up as well. Meaning the carbon drops a little bit in abundance. The oxygen goes up, which is now the third abundant element in the solar wind. If we keep continuing that, the other day I talked about the carbon and the oxygen becoming silicon, which is a very abundant element on the Earth. Before silicon and just after silicon, those elements in the zigzag line are much less abundant already. That is because, I believe, due to how we started out. We get a helium, we get a carbon. Those are the two building blocks. Not a beryllium, not a nitrogen, no, the first two. So a carbon and oxygen makes a silicon. Silicon's most abundant. Silicon is number 28. 28 total protons, nucleons if you will. Now we add 28 plus a 12, for example, carbon, we get calcium 40. Calcium, again, is a very abundant element. There are different pathways as well, so certain combinations I can make, all dependent on the circumstances that are there, meaning geological circumstances. What element is there? What other element is there? Those two together make the next element. So the abundance is a huge clue as to how the elements came to be. Nobody really talks about that. We can see in the abundance. We can find the clues for the reactions. That's kind of been the way I've been deciphering, if you will. Iron, right, iron. Iron was already touched upon with the fusion, fission, endothermic, exothermic reaction, meaning the lighter elements together usually create excess heat, an exothermic reaction. That's to say, until iron. There's the tipping point. That is a very common known fact, if you will. Above iron, the fusion doesn't yield energy anymore, but you use the energy. So what you end up with is basically iron. That's what nature strives for. If an element is heavier than iron, it would rather go back to iron, the most preferred state. If it's too light, it would want to go towards iron again, because that's what we end up with. So the Earth is created from mostly these elements. The most abundant elements are there. I think to top it off right now, and then I would like to invite you to ask all kinds of questions. Yeah, yeah. Oh, sure.
Ida, you were going to say something about the instant fossilization.
Oh, right, excuse me. I can touch on that too. You want to go first, James?
No, go ahead.
Abundance of elements, there are also elements to be found on Earth, specific isotopes that are not readily explained. I will give you a nice example. Argon 40. Argon is a noble gas. It is in our atmosphere at about 1%, right? It's a noble gas. Now we have what mainstream calls a missing noble gas problem. Where are all the other noble gases in our atmosphere? So rather, why are the noble gases not here, which are usually heavier than regular components of our air? Meaning they should be sitting here at the lowest part where we are in our atmosphere, should be loaded with noble gases, but they're not there. Nobody really knows what happened to them. Now when we look at an argon has three stable isotopes. With 36, 38, and with 40. So it's just a matter of the same element with some extra, what we call the neutrons. Remember, it's a proton plus electron. When we look at the isotope ratio, we see that the argon 40 is like 99% of the all the argon that is here in the air. How come argon is there? That's the first question. The neon is not really there. It's a little bit. The krypton is not really there, etc. But the argon is there, 1%, pretty much. Now we look at Mr. Louis Crevant, as Wallace likes to point out as well. We're talking biological transmutation, so how does that fit? We have a calcium 40, which is the normal calcium, and we have a potassium 40, as I pointed out with the chicken eggshell, right? So stop feeding calcium, still lays eggs with calcium. Oh, amazing. Stop feeding potassium, it doesn't make eggs anymore with calcium. Now these reactions, as I pointed out some of them on that poster over there, so later on if you want to, you can look at those reactions over there a bit more specific. But to get to the point, nature transmutates elements. The abundance of the elements contain the clues again, because the argon is there. The argon, I believe, is argon-40 specifically, which is a very strange isotope. It is stable, but it's a real strange one. I believe it's constantly created due to biological processes. So we see that the abundance of the elements, or cosmological model, if you will, biological plays an important role here, creating the elements again in situ on the Earth. So geological processes, biological processes, of course the things that mainstream already points out, they're there as well, but I don't think they're the dominant reactions. Life determines what elements are here, creating basically the building blocks it needs itself, right? If we have pretty Avebury, the ground was totally chalk, right, the white stuff. Yet the plants grow and have every element they need to do all the biology constantly. All the millions of reactions that happening in cells very fast, and yet all the elements are there. We don't see a real deficit, if you will. So that's amazing. Where do they come from all the time? So biological transmutations, I believe, are part of our cosmological model, creating the elements actually in situ. I think just talk now just for a moment.
So what I really find interesting about Edmund's approach is that he looks at nature and sees what nature is already doing, rather than looks at his model and thinks what his model will do. And this is kind of a weird way to do science, is to actually make observations first.
Oh my God.
And the book by Louis Kervran, which is Biological Transmutations, he also has another very interesting example. And this one shook my world about 3 weeks ago. Now this guy shakes my world like twice a week. But this one took a couple days to get over. And what happens is that in the desert, I'm American, so you may not, at 120 degrees Fahrenheit, which translates to something Celsius, right? It's much harder than your human body. So you have to somehow cool your body down to keep it below that temperature. And if you look at it, the main method they think that happens is with perspiration. But when you really do the calculations on how much water someone perspires, it doesn't work out. It turns out the body should get hot because the perspiration just isn't adequate. And what he believes is that the sodium that people take, you need sodium when you go out in the heat, is actually being transmuted into potassium. And he finds by looking at the urine of people out in the hot weather that they secrete a lot of potassium. And potassium is actually, it's a cold fusion reaction where you're going from a heavier element to a lighter element, meaning it's an endothermic reaction. It requires heat for that reaction to occur. So it's literally happening as you're doing cold fission in this case, and it's sucking heat out of your body. So a big part of your cooling process of the body is by this endothermic reaction. And if you think of ducks walking on ice, or I've always wondered how those little teeny legs can stay warm and not freeze, I suspect it's the exact opposite reaction, where they're actually doing nuclear reactions which are keeping them warm. So it's really a shock to me. Now, and that's kind of why I now look out at the world, and I see transmutations just going on everywhere now.
Could you just tell me about the instant fossilization?
So, yeah.
Cool, yeah.
Cool. Instant fossilization.
Here's the
Normal biology is made up predominantly of carbon and oxygen. Now, these are just quick numbers now. About 30% of our body is carbon, about 60% is oxygen, and we have a couple of percent of the other elements. If you assume that carbon and oxygen can become a silicon, and we put that, those ratios in from the human body, and we go to a biblical story, for example, some person looking back at some event and turning into a pillar of salt. What's going on here? Peter Mandeljup from Australia had a whole presentation last year at the EU, I think it was last year, about talking about instant petrification. How the animals that were found, the mastodon that James put up on the slide, for example, is barely, you can't recognize it from the surrounding rock material. But if you play with the thought that the carbon and the oxygen becomes a silicon, and electricity does it, maybe it's not a strange idea suddenly that that biblical story may have some truth there. So, meaning catastrophic events could actually turn a lot of biology into silicon oxide, quartz. Petrified wood We see on the inside basically like a geode. You see beautiful clear crystals, and on the edge where the other elements are basically moved to the edge, it's where, and you get a crystallized thing. So a tree is suddenly more like a geode instead of a living thing. So put all this together, a new cosmological model starts to appear. They weren't created in merging neutron stars, exploding stars, etc. Some of that might be going on, but I think we need to look at Sapphire much more to explain that one. But there is a next step. The next step is geology, biology, etc. They are responsible for the creation of the elements. We are probably doing it. Biology is probably doing it everywhere. Geology is doing it. The story would become much more logical, I believe. So, what I'm saying here, of course, is a high speculation content, yet there's a whole body of work and observations and experimentations that are pointing towards this direction. So I would like to challenge everybody together that we really need to start finding some better, more specific answers here. Come up with maybe experiments that would confirm these reactions, right? We need much more clear data. It's very, very important. I think that's the most important we're trying to point out here right now. You can see the reaction here again. So, depending on the building blocks, the availability of the building blocks, the whole cycle process of from the star to the planets, you suddenly get a logical story. How come we have so much silicon oxide? How come we have fossils that are still voluminous? I mean, an animal which is allegedly petrified over a long period of time, or a tree, for example, over a long period of time, or an animal, they should be flat, right? That's the normal fossilization. It's basically just an imprint. The mud comes up on it, it presses it down, changes it a little bit. But these things are the same shape that they had. So there's no pressuring or anything, and yet it's completely silicon oxide. So I think there are many, too many to name clues pointing out that this is happening. The abundance that we start out with, it's a logical pattern. So a carbon and a silicon, a carbon and an oxygen makes a silicon. A silicon plus a carbon makes a calcium 40. But a silicon plus an oxygen makes a titanium 44. I don't see Monty, but I think he has titanium 44 in his experimental chamber. So Monty, if you're listening.
I'm listening.
There you go.
So are you saying, Ido, then that the plasma discharge is the catalyst?
No, the catalyst is the heavy element iron in the plasma. The plasma.
Well, she's back to fossilization.
Sorry, I was talking about
I beg your
fossilization.
pardon,
But
yeah.
yeah, but I mean, to get the silicon, whatever it was you
No.
said. But the geodes and...
What you get is because it's simply my body would be 30% carbon and the other 2/3 would be oxygen.
Yeah, but to
So-
turn you into a fossil...
Mm-hmm.
Sorry, I didn't mean to say that. That came out. But if you were exposed to plasma discharge, is that the catalyst that would fossilise?
An electric
Is that
effect, whatever it is,
Just
maybe,
to clarify.
yes, some kind of discharge effect would create that.
Okay.
Yes, but mind you, one more thing. Carbonate is CO3, sandstone, calcium carbonate. One C, one O becomes one silicon. I am left with 2 oxygens, which is exactly the abundance of quartz, silicon oxide, 2. Silicon dioxide, right? That's quartz. So, matches beautifully. So we can be turned into a geode. Careful with lighting.
Can I come in here, sir? If you go to the White Cliffs of Dover, right, you'll see all these huge masses of chalk, which is carbonate, calcium carbonate.
Yes.
Now, the standard explanation is this is made from the shells of billions and billions of small fish. Yeah. The standard model is that the calcium carbonate in the chalk is made from billions and billions of fish shells, yeah? And then they've all been compressed down. But when you look at it, it doesn't look like that. There are bands within it of silicate, which they say is from sponges. Right, so you get these lines of flint, in fact. So to produce all that calcium carbonate in large quantities, there must be some other process. So you'd like to comment on that?
I think both are true, right? sedimentation and depositing of all those algae and etc. in the oceans, that does happen. But when we see certain layers in our geological record, there are also layers there that contain no fossils at all, but still with the same material. Right? There are no fossils there.
Yeah.
Then the carbonates can be turned into a silicon oxide. I want to point to Avebury with the big stones. I asked a question, I can't remember, I think it was Noah, but it could be somebody else. I said, what are the stones made of? He said, sandstone. I went, okay, calcium carbonate, something like that.
You mean limestone?
Huh?
Limestone.
Limestone, excuse me,
Yeah.
limestone.
Oh.
So we
Then
had
he
that,
said
and then I
calcium
asked, and they said, well, they're pretty tough. And he said, yeah, but it contains a lot of silicon oxide. Well, that's not sandstone, that's quartz, right?
Yeah.
Granite, whatever. He goes, yeah, but it contains little thingies there, and it's quite a lot, and little nuggets of the silicon oxide there. I go, well, pointed out, you know, this reaction, and he goes, wow, that could be the case, you know. We need to find other explanations. We need to look at the abundance of the elements. We need to look at alchemy again to come to a true new cosmological model. Yeah, and don't want to be facetious, but the current model explaining how exploding stars end up in uranium and gold mines way, way at the edge of the Earth. It defies all logic until you start accepting that electricity and life is very much electric, right? So the mitochondria in the cells are one of the suspect places where transmutations could actually take place. Now, many of these things are speculations. Many are also shown to be true, at least in observation, sometimes even in experimentation, where we don't understand it yet, and we need far more data. So.
Yeah. Well, I was kind of saying in the lecture I gave about how we have to follow in the footsteps of nature.
Yes.
This was the old alchemical way, is that look how nature does it, and you try and do the same.
Exactly. Yes?
Yeah, so I've got a row of questions, best just to ask them all together, I think. First of all, just noticed that in Avebury there were sulfide or little objects, iron sulfide probably, on the surfaces of those stones. That's worth noting. Second thing, I think the issue of the very amorphous forms of chalk deposits is very important, and I don't know what standard geology says about that, but you know, the observation's right. You look at that, there's no evidence of animals in there, just like you look at basic oil, you know, out of the ground. There's no evidence of fossilized or any animals in there. Next thing is about testable ideas. The thing about sodium and turning into potassium, and you know, to cool one when you're that'll turn up in pissing and so on. That is eminently testable. You know, if you're prepared to get people to do that, you can measure what's going into somebody and what comes out, and that is a testable thing without even doing any you know, big experiments in the laboratory.
That was done by Louis Kerbrand. That's where he began to get this idea that
All right.
This is an existing knowledge base.
All right. Well, we could reproduce it. Then.
Well, it needs to be reproduced because Louis Crevin, first of all, he wasn't a physicist. If you were not really, I believe more biology. I believe. Not sure there.
All right.
But it's not very specific. Meaning these things need to be redone and then better.
Yeah. No.
And not just looking at elements, which everybody does. And I want to point that one out too. We need to look at the specific isotopes. Very important. But please continue, Peter.
Yeah. Okay. I'll say redo them so they become unarguable. And the one about carbon-12 and oxygen-16 making silica. I mean that could be, you know, as I said before, we could do that, and we ought to do that. Just another one about a word of warning. You pointed out that the volcanoes tend to occur where there's water, right? And therefore you're arguing that water is important. Now, I think your theory is probably correct, but the other argument would be, of course, that the volcanoes appear at the edges of continents because they can't come through continents. So, you know, standard models have an answer for that point. And the last thing is, abundances in the solar wind. If there's processes going on in the solar wind, which would be highly likely, then you should get different abundances, say near the sun, when you do measurements on the solar wind, as you would near Earth or near Jupiter and so on. Right. So those things could be done again, or are being done all the time if we wanted to look at the abundances recorded.
Well, if somebody, some way, or through connections, has good data on this specific field, I'm more than interested. I would love to get my hands on it.
Okay.
But on the other hand, there is very little data. We're dependent on all kinds of satellites, etc.
Just a question about abundance of oxygen in the atmosphere and all that. I mean, this mainstream, of course, says that the atmosphere started out as methane and you didn't get oxygen until plant processes came along and turned CO2 into oxygen. Is that all just myth, or is there anything you could say about that?
Well, I believe those reactions are real, right? So the plants replenish the atmosphere with some oxygen. But then again, we take it away and turn it into carbon dioxide again, right?
No, but I mean, what they say is that when oxygen originally came in through this process, and it killed off the previous forms of life that couldn't survive in oxygen. So I mean, that looks like evidence. Do they just make it up, or?
Can you go back to the Sun and Earth page? Sure. I'll go to astrophysics just for a moment. Stars start out with hydrogen and turn into helium, but mainly carbon. That's the key. It goes to carbon. Then those two, helium and carbon, become an oxygen. Now, when we look at the life phase of stars, they turn into white dwarfs in the end, usually, or the other floating variant, doesn't matter. But white dwarfs are predominantly created. White dwarfs have a huge amount of carbon and oxygen. You can all look it up on Wikipedia, etc. So those two are suddenly highly abundant in white dwarfs. When these things keep evolving, you can all look it up, you will see that the metal contents, like the magnesium, the calciums and the irons, start to increase. Now if we take a concept like a hot Venus coming into a solar system from, let's say, behind Jupiter or Saturn, just for argument's sake here, you get a white dwarf coming in, which is pretty hot, 25,000 Kelvin allegedly, comes into the solar system, it loses its charge effect. I can't explain that very well, but it loses its effect, the sun draws it away, right? A little roll here. But you end up with a planetary body with these kinds of elements, which is very terrestrial, very Earth-like, and very hot still. By the way, Venus has a huge amount of CO2, I believe.
Yeah.
What we see is basically an explanation of how planets could actually start come into being. Now, I'm not saying this is the only process, but far from it. But I believe this is a piece of the puzzle that is totally ignored. We need to start painting that part that's missing. So, when we look at stars, they evolve. They evolve in the abundance of the elements, they become heavier, 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 with certain elements being very much there, and that fits exactly an Earth-like system. So, just to throw it out there, I like doing this. Was the Earth a star before? Were we a star? Right? It fits the bill. I saw somebody back there.
Yeah, sometimes you find a lot, is it on? Okay. Can you explain at the, what we call, I suppose, anomalies, the ones we can't transmutate, like this selenium deficiency and iodine deficiency are well-described problems on soils which are selenium deficient and iodine deficient. And when you're God, how fast can we terraform Mars?
I'm sorry,
The
repeat that
current
last.
model takes way too long for anybody to want to go there in this generation or the next.
What did you say? How far in that?
How fast could you terraform Mars given your new
Oi.
Just do it.
It's sensible. Does your model explain why those
Well,
would be the natural problems for?
I'm not sure you can. I'm not sure you can, because does Mars retain that atmosphere that you're creating? Or does it?
Didn't he? Oh, sorry. The first question, which is my, the first question was my more important one. Does your model explain why transmutation would be difficult for some elements, particularly selenium and iodine, which are well described, soil deficiencies leading to, sick people basically and munted babies?
I think Louis Kerr-Brown had things to say about that,
Yeah.
particularly iodine.
Yes, I couldn't answer right here, right now,
Yes.
but to come forward a little bit, if we were to zoom in on that, That's the beauty of this model. When you zoom in on that, the model will start explaining to you what's going on, as long as you pay attention, right? So we can look at, study the structure of the nucleus. Now an iodine is almost a noble gas, so that's a pretty different thing. Most of the periodic table is a metal. How come, right? Well, if you look at it more specifically, not right now, you will start to understand why they're predominantly metals, because the almost noble gases are the non-metals, right? The oxygen, fluorine. Selene is already halfway almost. It's a pretty special thing there. So, yes, the deficiencies could very well be explained that way, that certain reactions we simply cannot do, or for whatever various reasons are there, right? So yes, I believe that connection can be made. I can't do it right here, right now. So. What's to point out?
And how fast are you going to terraform Mars? How long will it take you? That's we answered another time, but it's very popular. If you put that one out there as a 7-minute Instagram thing, or 1 minute, you get a lot of views.
I believe we can do anything we want. as
2.5
human beings in the
days.
end. But I also believe, is it even sensible?
7 days, yeah, it's got to be 7.
I need some rest.
Earth days.
I need some rest there too. One rest day.
NASA or the military will give you $1.3 million to do that.
I really couldn't begin to estimate that. I think it's very far away from our realistic possibilities right now. But then again,
Edo, I mean, one important thing is that Mars seems to be very rich in iron,
That's right.
which is, you were saying, that's kind of like the default.
so yes. So what? Okay, let's look at that away. Why does Mars not have water anymore? Maybe it's used up.
Maybe it never
Maybe the
did.
reactions are pretty much done, so it doesn't have much elements anymore to even transmit. Like I pointed out,
It's got to the end point pretty much.
it got to the end point, iron, which is the balance point, the tipping point. So it's used up. When you are lacking the lighter elements, the reactivity goes down, 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 and other very aspects are there too, to trigger reactions, etc. But when you're done with your building blocks, you can no longer do it, right? And not only that, I believe water, water, most special. When oxygen is the third abundant element in the solar wind, the first abundant element is hydrogen, H2O. Where does all the water go? Right? It's here on Earth and a few other, like 2 or 3 others in our solar system, and that is where the geological active processes like volcanoes happen. Look at the Earth, it's all water related. What's water? What's the water? The oxygen fusion. Oh, another one, methane. If I take off that oxygen and I leave some hydrogens there, they tend to bubble up and connect to the loose carbons and whatnot, and we get a CH4 bubbling up at fault lines. At fault lines that have a fixed sediment layer there, like Saudi Arabia or the North Sea. That's where we see the accumulation of gases and oil. That's where we see the accumulation of all kinds of heavy metal mines. It's always at fault lines related. Now this is a mainstream knowledge. Right, so they come bubbling up. I believe these Lenner process, this cold fusion stuff, is going underneath our feet constantly. But there are a lot of parameters that, of course, are important here. So maybe the Earth, through its magnetic field, and this is speculation, and maybe Walt can jump in here. Maybe the magnetic field can actually gather all that oxygen and hydrogen, combining into water. They must, in the end, when it cools down, if you will, the solar wind cools down, it would start to react. So, I think this is my contribution.
Can I ask one more?
Yeah, sure.
We're quite near Cornwall, and there's a lot of radon gas comes out of the ground in Cornwall, and there's all sorts of weird explanations or lack of them. I wondered if you had an explanation, because it might point towards some of your theories.
So when earthquake activity starts to increase, or magmatic, you see an increase in radon, correct?
One does, yeah.
Yeah. So that, well, it could be a side effect, of course, from kind of movements, shock waves, whatever. I'm not sure what's going on there, but radon usually is a decay product of uranium.
Yeah.
So we start with the uranium, that's created through whatever process. Then it starts to decay usually by emitting alpha particles, so you strip off heliums. And at that phase it falls back all the way to lead. That's where you find the lead mines. So the lead mines tend to be old uranium deposits. They were old, they all decayed, yeah, and we're left with uranium. Halfway that process is radon. So, if you see more radon, there's more going on. Put in an electric component, telluric currents, etc. I think that would be a precursor indeed then, you know, for geologic activity.
But for you then, this is just a decay product. It's not a new idea for fusion biology.
It's radon is most likely only created through that decay process. So it's probably not created through building, but this happens a lot, by the way.
Okay.
You create a heavy element which is not stable, the self-organizing system falls back until it's stable, and then it can usually reach a noble gaseous state. Creating a noble gas by just putting things together in this model would be very difficult. So I think it's predominantly a decay result. Questions?
Is that on? Yeah. I remember years ago talking to David Sarkeld, but he showed this fascinating paper dealing with halos in mica around nuclear particles rich in uranium, and where as the isotopes decayed, they were doing halo effects within the mica, within the granites. Now the thing that was most interesting to him about these halos was that some of them indicated that rather than fission leading to the decay, we also had halos indicating that there was fusion creating higher elements. Now I wondered if you know anything about this, would like to comment on it, or somebody else in the audience who knows more about it than I can remember, but there seemed to be there geological evidence of elemental transmutation in the fusion process which has been taking place.
Radio halos.
Yes.
Radio halos are, you find them in basically every stone, but granite, for example, has little zircon crystals, to the top of my mind, in them, which contain radio halos. It's quite interesting because what happens is, somehow, some way, you get little aggregations of uranium. Don't know why, but they're doing it. These things start to decay, and every decay step that I was alluding to, every step it makes, it shoots off usually in a helium particle, an alpha particle, a helium nucleus. Sometimes something else, doesn't matter. That is a very energetic thing, so it shoots out in all directions, creating little tunnels. Tunnels everywhere, like the sea urchin thing, what was it? Tunnels everywhere. That's your halo. But one decay step is one ring. The next decay step is energetically different or different particle in another ring. So what you can see is that there are 7 steps, I believe, from uranium to lead, down to lead. So you get uranium radio halo, which is decay process. You see multiple rings there. Now, then you can do your calculations, and you come to a very old age, millions of years. Now there are also radio halos that contain only 2 or 3 rings. And we know that what we are left with is lead again. And the only steps that are there, and this is very much confirmed, polonium is just above it. Polonium decays to bismuth, I believe, and decays to lead, I believe. Something to that effect, or even in between polonium step. Now these reactions that I just alluded to are seconds. Literally seconds, maybe a minute or 2. Tops. How can you concentrate all that polonium into a little nucleus there, little grouping there, and only then it starts to decay, creating those specific few rings around it? That defies all logic completely, unless they were created in situ, that polonium over there. And that indicates an age of the creationists, 3,000, 4,000, 4,000, 5,000 years in granite. You can even find these halos, by the way, in diamonds, in kimberlite pipes. So radio halos, I believe, if we look at them properly, with this kind of knowledge, they are very valuable tools, but they also prove that the dating mechanism very wrong. But of course we cannot go there because that would mess up a lot of contemporary science, right? So therefore this is a pretty taboo topic. I think. The radio halos are a very important thing to study. So this, yeah, there you go.
Thank you.
One thing that struck me is if you're doing alchemy, there's 4 major steps.
Microphone.
Yeah. You got a microphone, anyone?
Yeah.
Right. If you're doing alchemy, you've got 4 major steps you have to take. You have to get your primer materia, and that's always the big secret. What the hell is the primer materia? And they argue endlessly about what you should start with. But then you have to push it through a process called nigredo to turn it into a black stuff. So you have to. The first stage is you make it into something black, a black lump. Well, that struck me. Carbon. Could be carbon, couldn't it? The first stage, or maybe it's ferrous oxide, because that's also black.
You're spot on here. So okay, let's go there.
And then you have to go. You've got to go to the next stage, which is called the peacock's tail, right? Which is multicoloured. And you're looking. They're always watching the thing, you know, and they observe it. They're real observers, and they see lots of colours appearing in their flask. And that's the second stage, the peacock's tail. I wonder if that's something to do with chromium, maybe, because that produces many different colours. And then your third stage is your white stone. The word stone is not lapis, it's calculus. And a calculus is really just a lump, isn't it? It's not really a crystal. And you have this white stuff which you can grind up and you can project it, and it will turn stuff into silver. So you're doing pretty well when you've got to there. Is this really working? Oh, I'm not talking into it straight enough. And then you can transform that into your red stone, your red calculus, which you can project, and that will make your gold. So all these stages, I mean red stuff, I wonder what that is. Is that mercuric oxide maybe? I don't know. But it seems that they're following some kind of pathway similar to what you're saying. But they're very patient. They're willing to take a year or more over this process. They keep the fire going to supply the heat that's needed, and just never let the fire go out. You know, you've got to keep it going. So I think there's a lot to be understood if we went back and looked at alchemy again from this point of view.
Okay. Gold, making gold, right?
Gold, that's what we want, isn't it?
Okay.
But the other thing is, you always find gold where there's been volcanoes.
So, make gold. From mercury to gold, right?
Or from whatever,
from
carbon
lead
to gold.
lead to gold.
Yeah.
I'll bring up the period, James, bring up the period table for us.
Yeah.
Gold.
Gold, yeah.
Iridium, platinum, gold, mercury, thallium, lead, bismuth, polonium, radon here, right?
Yeah.
Okay. If we want to make, I'm going to do it like this, sorry. If you want to make gold from lead, you need to reduce.
Yeah.
It's not feasible, very feasible. Not only that, if you want to make gold from platinum, you just need to add a little bit.
Yeah, well, platinum's more valuable, so you wouldn't want to do that.
You wouldn't want to do that. Mercury, maybe.
Yeah.
Reduce it a little, one step, right? Only one element away. Mercury to gold. You need to reduce it. These reactions are not easy to be done. It's not easy to be done. So, coming back to your observation there. What if I come from tungsten, and I add from tungsten an oxygen or an oxygen and a carbon? Not sure there, I haven't done the math yet. From tungsten, you can go in one step, boom, then you reach the gold. That would be your last step in what you just described, right?
Yeah.
So there are pathways to create a specific element. You have a specific pathway. Carbon, oxygen becomes silicon, plus carbon becomes calcium. But if you take an oxygen, it becomes a titanium. Now certain elements have multiple routes, meaning more readily made, much more made. There's your abundance again. The abundance is important. So I do believe that you can make stuff by adding heavier elements than hydrogens, right?
Yeah.
Right now we only think, I'll shoot one proton at it, one neutron at it, and that's our fusion mechanisms we're using, particle accelerators, etc. It's a limited mindset, it's not an alchemic mindset, so maybe we do need to go back to the alchemy indeed, yes.
Yeah. Okay. Oh, tungsten, right.
Tungsten was just.
Well, we got all those light bulbs. Old light bulbs. I can tell you some old light bulbs.
One of the things we would like to do is to create a new periodic table. It'll still have the basic structure, but it would show these pathways where certain elements combine with other elements, and it would be a three-dimensional periodic table, basically. But we first have to figure out the
The
elements.
new alchemist periodic table. Universe
Yeah, but
alchemy periodic table.
I would like to make one final comment myself. This is my plea, and basically to everybody. We need to start studying the elements. Very, very, very much. They contain so much information and truth, I believe. When we make that a new science again, or a specific part of science, so instead of only chemists or physics or biologists, we should have people that study the elements. When we know the atomic structure, we know a whole lot more, and we can do a whole lot more. So that's I just wanted to throw that one out still. Okay.